Imagine a place where gravity is king, ruling with an iron fist. So strong is its grip that nothing, not even light, the fastest thing in the universe can escape its clutches. That, my friends, is a black hole. It's more like a region of space-time so warped by gravity that it collapses in on itself, forming what we call a singularity. This singularity is thought to be a point of infinite density, a mind-boggling concept that we're still trying to wrap our heads around. But here's the thing. We can actually see a black hole directly. So how do we even know they exist? Well, we can observe their effects on their surroundings, the way they warp starlight, the way they influence the orbits of nearby stars, and the powerful jets of energy they sometimes blast out into space. The concept of black holes has been tantalizing astronomers and physicists for centuries. Way back in 1783, John Michell, an English clergyman and natural philosopher, first proposed the idea of dark stars, massive objects so dense that their escape velocity would exceed the speed of light. It wasn't until Albert Einstein revolutionized our understanding of gravity with his theory of general relativity in the early 20th century that the idea of black holes gained more traction. Einstein's theory predicted that gravity is not a force, but a curvature in the fabric of space-time caused by massive objects. It wasn't until the mid-20th century, with advancements in observational astronomy and theoretical physics, that evidence for the existence of black holes began to mount. Black holes come in a variety of sizes, from the relatively small to the mind-bogglingly massive. On the smaller end of the spectrum, we have stellar black holes. These are formed when a massive star, much more massive than our Sun, reaches the end of its life and collapses under its own gravity. But black holes can grow much, much larger. Lurking at the centers of most galaxies, including our own Milky Way, are supermassive black holes. These cosmic behemoths can have masses millions, even billions, of times that of our Sun. As we continue to explore the universe, we're likely to uncover even more secrets about the diversity and evolution of these fascinating objects. Now, you might be wondering, just how far away are these cosmic monsters? Well, the closest known black hole to Earth is V616 Monocerotis, or V616 Mon for short. This stellar black hole is estimated to be about 3 times the mass of our Sun, and it's located roughly 3,000 light-years away from us in the constellation Monoceros, V616. Mon is part of a binary system, meaning it's locked in a gravitational dance with a companion star. Astronomers have been studying V616 Mon and other nearby black hole systems like it to learn more about the physics of these extreme objects and their effects on their surroundings. Black holes are known for their insatiable appetites. They're like the cosmic vacuum cleaners we mentioned earlier, but instead of dust bunnies, they feast on anything that gets too close: stars, gas clouds, even other black holes. As material falls toward a black hole, it spirals inward, forming what's called an accretion disk. This disk of gas and dust heats up due to friction and gravitational forces, emitting intense radiation across the electromagnetic spectrum. As the material in the accretion disk gets closer and closer to the black hole, it reaches incredible speeds, approaching the speed of light. It's a cosmic cycle of growth and consumption, with black holes playing a key role in shaping the evolution of galaxies. One of the most mind-bending consequences of Einstein's general relativity is the idea that gravity affects the flow of time. And nowhere is this effect more pronounced than near a black hole. You see, time is relative. It's not some absolute, unchanging entity that ticks away at the same rate for everyone everywhere in the universe. Instead, time is affected by gravity. The stronger the gravitational pull, the slower time flows. As you approach this gravitational abyss, time for you would begin to slow down relative to time for someone back on Earth. This phenomenon is known as gravitational time dilation. Now, imagine you're that astronaut falling towards a black hole. As you get closer and closer, you would eventually reach a point of no return, a boundary in space-time known as the event horizon. The event horizon is the defining feature of a black hole, the point beyond which gravity's grip is so strong that nothing, not even light, can escape. It's like a cosmic trapdoor. Once you cross it, there's no coming back. Now, the interesting thing about the event horizon is that it's not a physical surface. You wouldn't crash into it or feel anything as you crossed it. From the outside, anything that crosses the event horizon would appear to freeze in time, its image forever redshifted as it's stretched and distorted by the extreme gravity. While black holes are known for their insatiable appetites, they're not always efficient eaters. As material spirals inward towards the event horizon, some of it gets blasted back out into space in the form of powerful jets of particles and radiation. These jets, known as relativistic jets, are thought to be powered by the black hole's spin and magnetic fields. As material gets channeled along the black hole's axis of rotation, it gets heated to millions of degrees and accelerated to near the speed of light. These jets can extend for thousands of light years, far beyond the galaxy in which the black hole resides. Astronomers have observed these relativistic jets emanating from supermassive black holes at the centers of galaxies, and they continue to study them to understand the complex processes that drive these powerful cosmic eruptions. Now, we've talked about stellar black holes and supermassive black holes, but let's talk about a real monster, TON 618, the largest known black hole in the observable universe. This behemoth tips the cosmic scales at a mind-boggling 66 billion times the mass of our Sun. To put that in perspective, that's like cramming the mass of several thousand Milky Way galaxies into a single object. TON 618 is so massive that it's classified as an ultramassive black hole, a rare breed of black hole that pushes the boundaries of our understanding of these extreme objects. It's located about 18.2 billion light-years away from Earth, in the constellation Canes Venatici. The discovery of TON 618 and other ultramassive black holes like it continues to challenge our theories of black hole formation and evolution. Black holes, despite their enigmatic nature, are not just cosmic oddities. They play a crucial role in the evolution of galaxies and the universe as a whole. For starters, supermassive black holes at the centers of galaxies are thought to regulate star formation. Their powerful gravitational influence can trigger the collapse of gas clouds, leading to the birth of new stars. But black holes can also stifle star formation by heating up surrounding gas and preventing it from cooling and collapsing. Moreover, the mergers of black holes, especially supermassive ones, can send shockwaves through the fabric of space-time, creating ripples known as gravitational waves. Studying black holes and their effects on the cosmos helps us to understand the fundamental laws of physics and the processes that have shaped the universe we see today. And if you enjoyed this video, check out why we haven't returned to the moon.